Welcome back. In this video, I'm going to solve exercises 20 to 23 of chapter 1. Exercise 20, it's a small exercise on the concept of a topological space that we introduced in the lectures, but we didn't give sufficient examples. So this is an example. So we have a 5-point set, A, B, C, D, E, and we declare the open sets to be one of these 8 sets actually. So the empty set, the whole space, singleton A, AB, AC, ACD, ABCD, and ABC. Now, we are not asking to show that this is a topology, because it's to write it, it's a little bit cumbersome to write it, lengthy, but you can check mentally at least that it satisfies the 3 properties of a topology. So it contains the empty set and the whole space, always. And if you take any 2 elements or 3 elements in this collection, their union is still in the collection. So if you take AB and AC, for example, the union is ABC, it's in the collection. If you take the intersection, it's A, it's in the collection. Okay? If you take AB and ACD, then the union is ABCD, and the intersection is A again. So you can try all the combinations. There are so many of them. But note that if I didn't include ABC in the collection, then this wouldn't be a topology, because it would not be stable under unions. Okay. Now here, finite unions, or everything is finite here, so there's no need to worry about this condition. Okay, so once we have the notion of a topology, or the notion of an open set, all the other concepts that we studied can be defined. So a closed set, a set is closed if its complement is open. Okay, so let us find the closed subsets of X. So I take the open set and the open sets, and I take their complements. So the complement of the empty set is the whole space X. The complement of X is an empty set. The complement of A is B, C, D, E, and so on. So we notice that there are exactly as many closed sets as open sets, okay? Because they are in bijection actually. So if you have 8 open sets, then we should have 8 closed sets. Okay, second question, find the closure of the singleton A, singleton B, and the set C. So by definition, the closure of a set is the smallest closed set of X containing the singleton A. So if you look at the list of all closed sets, there's only one closed set that contains A, which is the whole space. So the smallest one is X. So the closure of A is X. Okay, and what are the closed sets containing B? So we have B, C, D, E, B, D, E, and B, E, and X, of course. What is the smallest among these 4? It's just B, E. So the closure of B is B. What about CE? What are the sets containing CE? So we have the whole space, BCDE, CDE, and that's all. So the smallest one among these 3 is CD. So the closure of CE is CD. Okay. Third question, find all the neighborhoods of C. So let us split this question into 2 parts. So let us first find the open neighborhoods, which are by definition the open sets containing C. So I look at the list of open sets that contains C. So we have the whole space, AC, ACD, ABCD, and ABC. So there are 5 open neighborhoods of C. Okay. Now any set containing these sets, these 5 sets, is also a neighborhood. Okay, so I have to add actually 3 more non-open sets. So in addition to these 5, you have ACE. Okay, we add just E to AC. D is already there. ABCE, just we add E to the set, and we have ACDE, just at E. So these are the only possibilities. Okay, so there are 8 neighborhoods of C. 5 of them are closed, and 3 of them, 5 of them being open, and 3 of them not open. Okay. Last question, we have to find the interior, the closure, and the boundary of A, which is ABC. Now, ABC is in the list, so it's open. So it's equal to its interior, because the interior is the biggest open set contained in this set. So the set is open if and only if it's equal to its interior. Now, what is the closure of A? So I have to go back to this collection of closed sets. What are the closed sets? What are the elements in this list that contain ABC? Only X, actually. So the closure of ABC, or of capital A, is X. And this is not a surprise, because ABC contains A, and A is dense. So if the closure of A is X, then the closure of the bigger one is also X. Okay, so any set containing a dense set is itself dense. Okay, so the boundary is just the difference. So, and it's just DE. This is the boundary. Okay, so this concludes exercise 20. Exercise 21, an exercise about topologically equivalent distances. So we are given a metric space xd, and you define a new function of 2 variables related to d by this equation. D prime of xy is len of 1 plus dxy. So we have to show first that it's a distance, and second that it's topologically equivalent to d, and then you have to find the pole of center 0 and radius 1 with respect to d prime in the special case where we take x equal r and d the usual distance. Okay, so we have to prove the 4 properties of a distance. So non-negativity. Why it is non-negative? It's important, actually, because since d is non-negative, then 1 plus d is bigger or equal than 1. And when I take the len, since len is increasing, so len of 1 plus d is bigger or equal than len of 1, which is 0. So d prime is non-negative. Now, when it is exactly equal to 0, it's exactly equal to 0 when the len of 1 plus d is 0, and this happens when what is inside the len is equal to 1, because len vanishes only at 1. And this happens if and only if dxy equals 0. And since d is a distance, then this happens if and only if x equal y. Symmetry is straightforward, just go back to the definition. So we use the symmetry of d to prove the symmetry of d prime. Okay, so these are straightforward. Triangle inequality, less trivial. So once again, if we don't know where to start from, we write what we want to prove and try to do a sequence of equivalences to see where this leads us. So let us write the triangle inequality for d prime. Okay, I'm not saying that this is true, but I want to prove that this is true. So let us transform it a little bit. So I go back to the definition of d prime. Okay, so d prime is len of 1 plus d. So replace everything. And now the sum of the lens is the len of the product, as you know. Okay, so this right-hand side is just len of the product. Now, since len is increasing strictly, then the argument of the len here is less or equal than the argument of the len here. Or if you like, take the exponential, because the exponential is strictly increasing. So this is equivalent actually to saying that 1 plus dxz is less or equal than this product. And now we can develop this product. So we get 1 plus dxy plus dyz plus the product of dx and dyz. Okay, now subtract 1, and you get this inequality. So this is equivalent actually to the original one. Now, is this true? Of course, because d is a distance, so d satisfies the triangle inequality. So dxz is less or equal than dxy plus dyz. And of course, it's when I add in a non-negative term, so this is less than this. Okay. So if you like, dxz is less than this sum, and this sum is less than dxy plus dyz plus the product. Okay, so since this is true, this is true. So we have the triangle inequality for d prime, and therefore d prime is a distance. Second question, we have to prove topological equivalence. Now, you should notice that len of one, sorry, there was an error here. Len of 1 plus t is less or equal than t. This is a known inequality, and there are several ways to prove it. I will present 3 of them. Okay, so correct that, it's less or equal. Okay, first proof, consider the difference between len of 1 plus t and t. So this is a differentiable function. So when you take the derivative, you get 1 over 1 plus t minus 1. And 1 over 1 plus t is less or equal than 1 because you are dividing by something bigger. Since t is positive, then 1 over 1 plus t is less or equal than 1. So the difference is less or equal than 0. So phi is decreasing or non-increasing, if you like. So this means that we should change the order. So if t is greater or equal than 0, then phi of t is less or equal than phi of 0. But phi of 0 is just len of 1 minus 0, so it's 0. And we get len of 1 plus t is less or equal than t. So this is a quick proof. Another proof, since the exponential is strictly increasing, this inequality, so this is less or equal once again. So taking the exponential, we get 1 plus t is less or equal than et. And here again, you have at least 2 ways to prove this. Either we study the variation of the function et minus 1 plus t, or we use the Maclaurin series of t. So we know that e to the t is 1 plus t squared over 2 factorial plus t cubed over 3 factorial plus so on. And since t is non-negative, all these terms are positive. So this series is bigger or equal than 1 plus t. Okay? Now, third way is geometric. We know that the len is concave, so it's below its tangent at any point. So in particular, if you take the tangent at 0, the equation of the tangent at 0 is just f of 0 plus f prime 0 times t minus 0. Now, what is f of 0? F of 0 is 0, and f prime, as we noted, is 1. So we get len of 1 plus t is less or equal than t. Okay, so you can draw a picture if you like. Now, this is not the len, this is the shifted len, so it vanishes at 0. Okay, it's not minus infinity. So it's minus infinity at minus 1. So we shift everything to the left by 1. Okay, so having said this, then it follows that d prime is less than d. And from this, we can directly conclude that the topology generated by d prime is contained in the topology generated by d. Or if you like, in another way, every open set for d prime is an open set for d. Okay. Now, if you didn't notice this inequality, you can always solve the problem without proving this inequality. But by the way, it's very important to master these techniques of proofs, because especially if you want to teach in schools someday, it's very important to master these geometric and analytic techniques of proving inequalities. But now, if you didn't notice that, it's not a big deal. We follow the methodology that I explained in the lectures. So to prove that Td prime is contained in Td, we have to prove this condition. For every x in the space, for every positive number r, there exists a positive number alpha such that the ball with respect to d of center x and radius alpha is contained in the ball with respect to d prime of center x and radius r. Okay, so we have a ball inside a ball with the same center. Okay, so let us rewrite this. So I dropped the quantifiers here in order to make it simpler. So for every x, for every r, there exists alpha. What does it mean that this? How to write this inclusion in terms of belonging? So any y here is here. So any y in this ball is in this ball. So it means that whenever the distance d between x and y is less than alpha, the distance d prime between x and y is less than r. So this is equivalent to the following implication, but I dropped the quantifiers in order to make it simpler. And now I go back, I replace d prime by its value. So I have to, so this condition is equivalent to this implication. dxy less than alpha, we don't know what is alpha because we are searching for it. Now we will see when this is holds. Okay, but we are just writing the condition. So dxy less than alpha implies len of 1 plus dxy less than r. And now this inequality, if I take the exponential, so I get rid of the len, take the exponential and subtract 1, this inequality is equivalent to dxy less than er minus 1. So we have dxy less than alpha implies dxy less than er minus 1. Okay, so when is this true? It's true if we take alpha equal to er minus 1 or anything less. So we can take any numbers. We can take er minus 1 over 2 if we like. And of course, this quantity is strictly positive because r is positive. So the exponential is strictly bigger than 1. Okay, so this is another proof that TD prime is contained in TD. And note once again, we flipped the order. So the biggest topology corresponds to the smaller ball. Okay, and not the other one. So, but we have D prime less or equal than D. Okay, reverse inclusion. So we do the same thing, but now we flip the order. So to prove that TD is contained in D prime, we have the same thing, but with D and D prime reversed. So once again, this is equivalent to D prime less than alpha implies D less than R. And I replace D prime by its value, take the exponential, subtract 1, so you get this condition. For every x, for every r, there is just alpha such that this is true. And when is this true? It's enough to take e alpha minus 1 equal r. But when I solve this equation in alpha, I get alpha equal len of 1 plus r. Okay? So this condition is satisfied. For every r, there is alpha that could be taken len of 1 plus r or anything smaller actually. And therefore, we have the reverse inclusion. So the two distances are topologically equivalent because they generate the same topology. Okay, last question. Very simple. We take now D to be the usual distance on R, and we have to find the ball with respect to D prime of center 0 and radius 1. So we try to see when a point belongs to the ball with respect to D prime. So a point belongs to this ball if and only if D prime of x, the distance from x to the center, is less than the radius. But D prime of x and 0 is by definition len of 1 plus absolute value of x minus 0, which is just absolute x. And this is less than 1 if and only if what is inside the len is less than the e, the exponential number. So 1 plus absolute x is less than e is equivalent to saying absolute x is less than e minus 1. And this means that x is between 1 minus e and e minus 1. Okay, so the ball is just this interval 1 minus e, e minus 1 open. Okay, so this concludes exercise 21 that we asked some years ago in the exam. Next exercise, same spirit, we have a metric space and we set rho of xy to be d over 1 plus d. So this is very similar to the example that we did in the lectures when we took rho to be minimum of 1 and d. This is very similar. So we have first to prove that it's a distance, but we are guided. Now, the first three properties of a distance are straightforward. So only the triangle inequality is not trivial actually. So the first two intermediate question is to help you prove the triangle inequality. Okay, so we start by studying the variation of the function given by f of t equal t over 1 plus t. So we have to show that it's increasing and it's what we call sublinear. Okay. And then you'll use that to deduce that rho is a distance. And finally, you have to show that they are topologically equivalent. So the easiest thing to do is to take the derivative. And when you take the derivative, you get something positive. So f is increasing. But there's another method, actually, more algebraic, that doesn't involve derivatives. Just rewrite f of t as 1 minus 1 over 1 plus t. So just add and subtract 1 in the denominator. Okay, and now what do we have here? We have, so 1 over 1 plus t is decreasing because it's an inverse, but when we take the minus, it's increasing again. Okay, so if a is less than b, then 1 plus a is less than 1 plus b. So when I take the inverse, because everything is positive here, 1 over 1 plus b is less than 1 over 1 plus a. And when I take the minus again, minus sign again, I flip the order. So I flip twice the order. So I get the correct order finally. Okay. So and then I add 1, and then this means that f of a is strictly less than f of b, so f is increasing. Okay, this is an algebraic proof. Okay, second question. Why f is sublinear? I just go back to the definition and I split my fraction into 2. So just a over 1 plus a plus b over 1 plus a plus b. Now 1 plus a plus b, since everything is positive here, 1 plus a plus b is bigger or equal than 1 plus a. So when I take the inverse, I get something smaller. So the first term is actually less than a over 1 plus a, because the denominator here is bigger. And same thing for the second term. And I get finally f of a plus f of b. Okay, and now I'll use that to prove that rho is a distance. Now, it should be clear. By now, you should be able to write them with no difficulty. But in the exam, you have to write them, okay? Even if they are trivial. So, non-negative, it's 0 if and only if x equal y, and symmetric. They should be obvious. Now, the triangle inequality actually follows from what we said. So first, I write the triangle inequality for D. And then, since f is increasing, I take the image of each side. So f of dxz is less or equal than f dxy plus dyz. But by question B, f is sublinear. So f of the sum is less than the sum of the f. So I get f of dxz is less than f of dxy plus f of dyz. And f of dxz is just rho. F of d is rho by definition. So I get rho of xz is less than the sum of the f's, which is just rho of xy plus rho of yz. And this is just the triangle inequality for rho. Okay. Now, why they are topologically equivalent? Okay, just have to observe first that rho is less or equal than d, because we are dividing d by something bigger than 1 or equal. So rho is less than d, and therefore from this we can directly conclude that t rho is contained in t. Now, for the reverse inclusion, we write the condition that we want to prove that we explained in the lectures. And it's equivalent to saying that if rho of xy less than alpha implies d of xy less than r, but rho of xy is just f of dxy. And since f is increasing strictly, this inequality dxy less than r is equivalent to saying that f of dxy less than f of r, because f is increasing. So you notice that here we have the same number. So it's enough to take alpha equal f of r, which is just r over 1 plus r. Or anything smaller would do, but should be positive, of course. Okay, and so this proves the reverse. So this proves that TD is contained in T rho, okay, the other way around. So we have equality, and therefore D and rho are topologically equivalent. Okay, we asked this also in an exam some years ago. Last exercise, also about topologically equivalent distances. On R, we consider d bar to be the difference between arctangent x and arctangent y in absolute value. So we have to show that d bar is a distance, and it's topologically equivalent to the usual distance, which is just I denote by d. Now, by now we should be able to prove that d bar is distance because we did so many examples. So we have to prove the 4 properties. Even here, the triangle inequality is straightforward because you just add and subtract arctangent z, or if you like. So just write it. Okay, straightforward. Now, I only prove that they are topologically equivalent, but here it happens that d bar is less than d. Why? Because if I consider f to be the arctangent function, then its derivative is 1 plus t squared, and in absolute value it's less than 1. So by the mean value theorem, f is Lipschitz continuous with constant 1, as you know. So, but d bar is just f of x minus f of y. Okay, so this means that d bar is less than d, And therefore, from this, I conclude that the topology generated by D bar is contained in the topology generated by D. And here we have the same order. Okay. Now, for the converse, we do as usual. For every x, to prove that TD is contained in TD bar, we know by the methodology that we explained in the lectures that this is equivalent to this condition. Okay? So, and this is equivalent to saying for every x in x, for every r positive, there is alpha positive, such that for every y, if d bar xy less than alpha, then dxy less than alpha, and I replace everything by their value. So I have to prove this condition. For every x in x, for every r positive, there is alpha positive, such that if arc tangent x minus arc tangent y is less than alpha in absolute value, then x minus y in absolute value is less than r. And is that true? Yes. Why it is true? Because this is just a consequence of the continuity of the tangent function at the point arc tangent. So if you write the condition of continuity in terms of, if you go back to the definition of continuity with epsilon delta, here we can, by the way, you can put instead of r epsilon, doesn't change anything. Okay, so if you write the condition of continuity of tangent t at the point, for example, call it t0. So take t0 equal arc tangent x. So we find a number alpha such that t minus t0 less than alpha implies tangent t minus tangent t0 less than r, or epsilon. And so now replace t bar arc tangent y and t0 bar arc tangent x, you get precisely this, okay? Because tangent of arc tangent is the argument itself. So this is a consequence of the continuity of the function tangent. And if you didn't get well this argument, don't worry, because we'll study continuity in depth in the next chapter. But in principle, you encountered the definition of continuity in first year. So this is just a consequence of continuity. So this proves that D and D bar are topologically equivalent. And this concludes exercise 23 and the video as well. So thank you for your attention and see you next time.